Welcome to the Aerospace Advantage podcast, brought to you by PenFed. I'm your host, Heather Lucky Penney. Here on the Aerospace Advantage, we speak with leaders in the DoD, industry, and other subject matter experts to explore the intersection of strategy, operational concepts, technology, and policy when it comes to air and space power. So today, we're talking about space launch. Here at the Aerospace Advantage, we talk a lot about space superiority, but let's face it, you can't have space superiority if you can't get to space. So assured access is critical. Can't believe it, but the United States is on track by the end of 2024 to have over 120 launches. That's a really impressive number, but don't get too excited. The overwhelming majority of those are SpaceX launches to support the Starlink constellation. SpaceX is launching on average every 2.9 days. And they must, because when it comes to medium and heavy lift, for almost all of 2024, they were the only game in town. Further, most of those launches occurred out of the Eastern range. So while SpaceX launch rates and reduction in launch costs have been game-changing, the reliance on any single provider is never a good idea. So what can the United States do to increase the pool of launch providers and launch locations? Well, that's what we're here to discuss today. And to help us walk through this important topic, we're happy to be joined by Brad Appel, the Chief Technology Officer at Ursa Major, the leading independent rocket propulsion provider. Brad, welcome. Thanks so much for joining us.
Thank you, Heather. It's great to be here.
And also joining us is one of Mitchell Institute's resident space experts, Charles Galbreath, and he just recently released a new policy paper looking at launch. Charles, welcome back and congratulations on the report.
Thanks, Heather. Great to be back. And thanks for the congratulations on the paper. Glad to be done with the editing phase
as always.
and move on to the publication and discussing this important topic.
Yeah, every report is an emotional journey for us, as well as an intellectual journey. I totally understand.
Absolutely.
So let's get started with you, Charles. I provided a high-level overview of launch, where SpaceX really has cornered the market. Can you expand on where we are as launch today?
Yeah, absolutely. So in the United States, and when I say the United States, I'm focusing on the Space Force from a military perspective, because that's what we do here at the Mitchell Institute, is focus on the military perspective. So within the Space Force, there's really two main avenues for launch capabilities. There's the National Security Space Launch, or NSSL, and there's the OSP-4, Orbital Services Program Launch Contract. So NSSL is primarily the medium and heavy lift boosters that deliver satellites to low Earth orbit or to higher orbits.
Okay.
The OSP-4 is for emerging capabilities, smaller launch vehicles that can do sort of a one-off small payload delivery to low Earth orbit.
And just kind of a more targeted capability.
It is a more targeted capability. If you think about it like travel, right, in the city. Here in DC, we have the metro, we have buses, we have Ubers and taxis. If you think about these larger lift, these mediums and heavies, as the metro train getting you from point A to point B, there's only a set number of locations where they'll drop you off and pick you up from.
Yeah.
Right.
Yeah.
Right. But if you want to get to a specific location, a specific orbit in this case, then you're going to be looking at a smaller launch provider or utilizing the entire medium or heavy booster, right? If you're that big of a payload. Okay. But as we're seeing, a lot of the payloads that are getting launched today are small, right? And in fact, the proliferation of small satellites can largely thank the availability of launch through SpaceX and the reduction in launch costs that we've seen. So within those two constructs of NNSL and OSP-4, there's families of capabilities. So obviously there's SpaceX for NSSL, but there's also a new entrant on the market, which is United Launch Alliance's Vulcan rocket. They just completed their second certification launch in early October. Unfortunately, the certification process is taking a little longer than expected. General Garant, the commander for Space Systems Command, recently announced that the certification process is slipping a bit further, and that two of the missions that were originally manifested for the end of 2024 have now slipped into 2025. So we hope that the process works through quickly and that Vulcan can become certified for NNSL launches in early 2025. There's also a third entrant, and that's Blue Origin. Blue Origin has not yet done a launch demonstration of their capability with the vehicle called New Glenn. So those are the three that we're looking at for NSSL.
Now that's heavy launch, right? That's medium to heavy.
Medium and heavy launch. That's right.
Okay. And so also just for our listeners and to get me up to speed as well, heavy launch or medium launch is really about the size of the rocket because you need to have a certain amount of fuel necessary to get a certain weight and payload to a specific orbit.
That's right. And so when I talk about medium or heavy launch, just to give you some ballpark figures, a Falcon 9 can get 22,800 kilograms to low Earth orbit.
Oh, come on. Talk to me in pounds, man. Weights and measures.
Oh, my gosh. That's one of the traditional challenges of space flight is kilograms and pounds. And there was a NASA mission that, anyway, that's just a benchmark, right? The ULA Vulcan is going to be delivering about 10,000 kilograms to low Earth orbit. When I talk about small launch, things like Rocket Lab's Electron or the Firefly's Alpha rocket, these are on the order of 1,000 to 1,100 kilograms.
Okay.
So an order of magnitude less.
Significantly less weight, which gives you more, I would think, agility and nimbleness in terms of where you could launch as well as the size of the rocket.
It gives you, because it can't launch as much or as many, you're probably going to have a bespoke launch trajectory. So it's going to go where you want it to.
Yeah.
As opposed to if you're a ride share on a Falcon 9, one of 50 or 60 or 100 different satellites, you're going to go where it wants to take you.
Where it's going to drop you
right?
off, yeah.
So where the metro train is going to drop you off, that's where it's going to put you. But if you want to go to a specific orbit at a specific inclination, a smaller launch vehicle, if it has the throw weight to get you there, is maybe a better option. And then just for comparison, since we're talking about orders of magnitude, Starship, which is getting a lot of press these days, it's a super heavy. We're talking about 100,000 kilograms to low Earth orbit. So another order of magnitude, or 5 times at least, leap in terms of what you're putting up in orbit. That can truly be a game changer. So when we talk about national security launch, we're looking at NSSL, OSP-4. We're talking about medium and heavy and small. And we're also now talking about super heavy.
Wow. Okay. So, Brad, Charles just provided this overview of launch providers, traditional and new entrants, and the different trajectories. Where does Ursa Major fit into this ecosystem?
So Ursa Major is a propulsion company, and we're fielding and developing propulsion products across a range of aerospace and defense arenas. Today includes solid rocket motors for small and medium missiles. It includes hypersonic engines, especially for test beds and targets and applications like that.
Hypersonics.
But launch is some of the roots of where our expertise really comes from. Dating back to when the company was founded in 2015. So for example, I joined Ursa Major a little over 6 years ago, and I came from SpaceX, where I led the development of the last several major block upgrades of the Merlin engine, which powers Falcon 9. And I was lucky to be there at a particular arc of time where we went from some very scrappy early high-risk missions all the way through figuring out landing and reuse from an engine perspective, in my case, and on to EELV, the precursor to NSSL certification and some NASA certification. So since I joined Ursa Major, we've had a lot of other experts join the company from all around the launch industry, spanning Starship and all kinds of these other vehicles we're talking about. And we're applying that expertise to launch rocket engines, but also many other propulsion systems. It's been a very, very wild ride. We just had our first launch of one of our engines earlier this year with Stratolaunch.
Congratulations.
Thank you. It was fully successful on the very first attempt, which is sort of a rare feat, rare stat to have in the sort of new space arena.
Yeah, absolutely.
It definitely is.
Yeah, the air launch liquid application is very interesting. It's interesting for me to contrast with the vertical 2-stage launch experience I had with Falcon.
Brad, if I can interrupt you, would you please describe for our listeners Stratolaunch? Because I'm familiar, but they might not be.
Sure, and they're in the hypersonics arena. They're a flying test bed where, for those that may be familiar with the challenges of developing hypersonic systems, you can't exactly just get a conventional wind tunnel and make it work. There's extreme enthalpies, extreme temperatures involved when you're going at those speeds at a particular altitude in the atmosphere. And so there's also, extremes of chemical kinetics involved. And so at the end of the day, just flying those speeds in the actual atmosphere is one of the best ways to develop systems there. And Stratolaunch is providing a very rare capability to do so.
Yeah, I mean, Stratolaunch is really, it's interesting. So it's an air-launched vehicle test bed, but it's two 747s that are knitted together, and they've got 6 engines. So this thing is really massive that you then, load up the payload, and it's a horizontal launch
Right.
that you then either can do hypersonic testing or can tip up and go vertical and go into space.
That's correct. The current mission focus there is hypersonics. From our propulsion perspective, the liquid rocket engine, which powers it, is extraordinarily similar to an orbital class rocket engine. And so the ConOps and the technology involved are very similar.
Yeah, super cool. So, getting back into the space launch piece, there's a critical distinction between the small launch and the medium and heavy and super heavy. And Charles, you and I talked about it a little bit, but could you both provide a little bit more insight regarding the key differences, whether or not that's from a launch location, technical challenges, or other elements that we should be thinking about when we consider these different types of launches?
There are all kinds of interesting capability differences between small, medium, heavy launch. And while the exact definition of payloads varies between them, a good way to think about it is small launch is sort of the minimum viable product of launch, right? So defined at the upper bound as 1,000 kilograms to low Earth orbit, there aren't too many useful payloads that are under maybe a few hundred kilograms. And so small launch is a logical first entry point for a startup company that wants to break into the launch industry. It may only take a few $100 million of capital investment to get a viable small launch vehicle.
Oh, wow.
Whereas when you graduate to medium and heavy launch, you're talking billions. It's a logical minimum viable product. And it has those advantages that Charles alluded to with, very dedicated, personalized, so to speak, orbital delivery. But the flip side of that is, the addressable market can be limited, right? You're not going to launch large satellites. You're not going to launch large quantities of rideshare missions. And some of the costs per kilogram metrics are going to be a little bit more challenging at that scale. You're on the other side of the economies of scale. So when you think about a launch vehicle, as with most systems, you have, fixed costs and variable costs. And so just to operate a launch vehicle, I've got a lot of people in a launch site and avionics and telemetry. And I have all these things that are cost regardless of the size of the vehicle. And so that tends to bias towards higher dollars per kilogram for a small launch vehicle. And then you also, what's interesting, another interesting trend to follow in the industry is reusability. Mm-hmm. And you're seeing a Falcon 9, on the upper side of medium or low side of heavy launch, obviously setting the example for reusability. In small launch, it tends to be more difficult. We're not seeing as many players there really being successful with reusability there. You have less performance margin fundamentally when you're reusing a vehicle, which of course is one of the best ways to drive down cost. You need to save some energy, some capability to return the first stage. And when you have a small launch vehicle, there's a little bit less margin to go around. So anyway, serves an important role in the industry, but I think medium launch it could be categorized as really the workhorse class. So that is Falcon 9. We have a lot of upcoming vehicles entering here in sort of that 10 to 20,000 kilogram bucket. Rocket Lab Neutron in development. Firefly and Northrop are teaming up on a medium launch vehicle as well, and that'll be exciting to see develop. And so that's also a class where reusability really starts to become viable. You can have margin to do so. And that gets into the technology side of the piece, right? It's not easy. You do have to be architect intentionally to make those systems reusable. But then, heavy, as Charles mentioned, Vulcan Centaur, when it's got all of the boosters on board, New Glenn, Starship, of course, there's only going to be a few organizations in the world with the capital to develop those systems. And you really have to be intentional with a heavy launch vehicle about what payload market you're going after. It's going to make sense for deploying a lot of constellation satellites, just a lot of mass that has to get up. It also can be capable of some high energy missions. Maybe there's some national security missions that have to go to pretty interesting orbits. The Centaur stage is really powerful for that type of application. So those are some of the kind of interesting technical and economic differences between the classes.
Yeah, Brad, thanks for bringing up cost, because you're right. There's a couple different ways to look at cost. There's the total dollar value of the launch vehicle, and that's typically not what people in the launch industry use. In my paper, I talk about low cost, and I did it as an absolute. And for small launch like Firefly you're looking about $15 million to $17 million for the booster. Compare that to roughly 67 to 70 million for a Falcon 9, about 110 for a Vulcan, and who knows what Starship will cost when they're actually offering rides on that. But again, the orders of magnitude difference in terms of costs. But you're right, it's the kilograms per dollar that we talk about to get to orbit. And so certainly something that's larger, it can carry more. And like you said, Brad, the per launch costs are then shared among that mass. So
the ride share,
kind of approach gets you a little economy of scale, if you will. There's another key aspect, and that's the launch locations. Primarily, NSSL missions launch out of Patrick Space Force Base on the eastern range or out of Vandenberg Space Force Base on the western range. The benefit of launching to the east is you get some of that rotational velocity of the Earth, and you can get a little more mass to orbit. And it certainly helps you when you're trying to get to the lower inclination.
I'd never thought about that. Leveraging the rotation of the Earth to help me get further into space.
Just a little bit.
That's still cool.
Right. Versus launching out of Vandenberg, where because of the geography of the coastline, you typically launch either due west or south into a polar orbit. Of course, that's very useful. So the medium and heavies will launch from those two launch sites.
Mm-hmm.
The smalls can also launch from there, but they have a couple other opportunities. There's Kodiak up in Alaska, where we've done some launches. And there's Wallops Island out of Virginia, where we've done launches for decades. And so the small launch vehicles, because they don't have as much noise, they don't have as much of a safety zone to watch out for, you have an increased ranges.
You've got a greater portfolio of locations that you can launch out of.
That's right.
So, it's funny that you mentioned that because flying little airplanes on the FAA charts, right, the aviation charts, the maps that I use, there are airports that are also designated as spaceports.
Yes, there are. And so I only talked about the 4 that are currently operational. There's Spaceport New Mexico, for example, that is definitely trying to get into not just the suborbital launch market, but also the orbital market. And so there are other suborbital launch locations across the country that people can be using.
But suborbital, that's essentially like, the Mercury missions, right? You're just kind of doing a ballistic trajectory.
To be clear, the very first Mercury mission.
Yeah, that's
right?
True. Yeah.
So that was a suborbital. The things that Jeff Bezos is currently doing with the New Shepard, right? So named after Alan Shepard, the first Mercury astronaut, those are suborbital. If they go up, they breach the boundary of space, the Kármán line, and then they re-enter. They don't actually complete a full orbit. But the orbital launches out of Patrick or out of Vandenberg or out of Kodiak or out of Wallops, those are actually achieving orbit.
So the suborbital launches, does their payload, does that remain suborbital? Or
It does.
Okay.
It does, because the key factor is achieving enough velocity to achieve orbit. It's not just about the height, it's the velocity.
Yeah.
PenFed checking and savings accounts are here for all your adventures. From...
Do you take this man to be your husband?
I do.
To...
He has your eyes.
He's perfect.
Learn more at PenFed.org. Federally insured by NCUA.
So we've had a great discussion here on sort of the science of launch, and I'd like to dive deeper into the technologies associated with launch and how they've actually shaped the launch market. And, Brad, you had brought up, this was really interesting and I hadn't thought as much about it, was the elements of margin in rocket design, whether or not that's structural to allow for reentry, the fact you have to hold back fuel to be able to control your reentry and do that kind of recovery. So I'd like to discuss some of those technologies more because it's literally rocket science, but we got to keep it at a higher level. Brad, let's start with you.
Yeah, a launch vehicle is one of the most interdisciplinary systems that you can imagine. If you just think about who's on mission console giving a go for a particular launch, flight termination, telemetry, avionics, obviously weather, propulsion. It's a massive engineering undertaking that makes it work. That said, there are some subsystems and technologies that are more sensitive drivers to things like schedule, risk, cost, and certainly reusability. And so reusability is where I think one of the most fascinating trends is for the industry. It's a very logical way to drive down cost and to increase cadence, because I can maybe work with a reduced production rate because I can reuse so much hardware. There's an interesting intersection between reusability and the cost buildup because of that penalty you pay to take the stage back. And, as a typical example for a two-stage vehicle, the first stage, which is the more achievable reusable element, might be something like 75% of the cost of the whole system. Now, this can vary a lot, vehicle to vehicle, but it's going to be more than half. In order to recover it, I have to save a certain amount of propellant and fuel to make the trip back, and I have to cancel out the velocity I've imparted to help the upper stage get where it's going, and then I might have to propulsively brake to cushion the heat loads during reentry, and I also might need to end up at a particular destination like a barge or a landing pad somewhere. So when you add that up, the energy penalty to payload, it tends to be maybe in that 30 to 50% kind of ballpark of I've relative to an expendable mission where I gave it every last drop of fuel for a cent. Mm-hmm. If I'm recovering the first stage, maybe I'm cutting 30 to 50% of payload capability out. But then so you can compare those two numbers. I might be saving if I can reuse the first stage countless times and amortize its cost to very low numbers. I'm saving 2/3 to 75% maybe of the cost. I'm delivering 30 to 50% less value. But then you kind of divide those ratios. I'm roughly still reducing the dollar per kilogram by about a factor of 2. So that's that kind of magnitude. Mm-hmm. Now, that said, not every technology can get there. In order to have the margin to come back and still deliver useful payloads to orbit, there are two technology elements that are the most sensitive to be able to do this. And one is the structural efficiency of the vehicle. And so this gets to tank material and construction method, the pressurization method, the propellant choice, kerosene, methane, hydrogen. Those tend to drive different volumetric efficiencies of the whole system. And then equally as important is the engine capability. So how fuel efficient, we call that specific impulse, is it? How weight efficient is the engine itself? All of these things directly affect your ability to reuse the first stage. And then when you're talking about second stage reuse, which hasn't been perfected yet, right? So SpaceX with Starship is trying. There are other firms out there going after it. It's a much more difficult technical task to reuse the second stage. You're coming back from orbit. There's way more intense velocities and heat loads to deal with. But you're also compounding that economic trade-off, right? I'm going to decrement my payload capability a little bit more than if I was just using the first stage for reentry. But I'm also saving some costs. And so that you kind of have to compound that trade. So whereas Falcon 9 has shown us that, first stage reusability seems to add up economically, second stage reuse is going to be a fascinating trend to watch in the coming years.
Well, and so second stage reusability is something we've seen before as well. The space shuttle, pretty impressive second stage there and its return capability. General Chilton would, of course, admonish me if I didn't
You're talking to my heart.
Remind folks that was out there a while back. And we can also look at the X-37 as a bit of an upper stage that's reusable as well. But you're right. There's a lot more technology that needs to be developed and demonstrated in order to fully realize, again, a reusable second stage. I wanted to just dive in on another little technology piece, and that is the manufacturing process for our rocket component parts. And so there's been advancements over the past 20, 30 years in terms of additive manufacturing, 3D printing, if you will, as well as new ways to construct metallic materials in order to have higher heat tolerances or to produce them in a way that's more viable for reusability, and also the testing and making sure that they're good to go for that next launch. And so I think there's some technology areas there that we're continuing to push the envelope on and make good progress to improve the reliability of our launch, reduce the costs, and really give us that assured access to the space that we need.
It's going to be really interesting to see where this technology and these innovations are going to drive us into the future. But our existing launch capability right now really shapes what we can have on orbit and the orbits that we can support. So, Charles, in your paper, you discuss the 4 C's: confidence, capacity, cadence, and cost. So how do these launch factors shape the space architecture that we have today?
Yeah, absolutely. So the architecture that we have had, call it the legacy system, where we have highly exquisite satellites that last, 10, 15 years on orbit. That's largely because the technology that we had to launch them was also expensive. And so if you're going to spend a decade to develop a satellite, you want to make sure that that launch vehicle is going to get it where you need. And so you have to have,
you can't afford for it to blow up.
Right. So you have to have high levels of assuredness in your launch provider as well. And so there's this little bit of a cycle that continues to increase cost and weight and delay delivery of vehicles. And that's why we had these exquisite systems, these what some have called fat, juicy targets. And now we're beginning to shift that architecture to a proliferated approach. Well, one of the things that enabled that proliferation is the availability of affordable launch.
Yeah.
And certainly the reusability that Brad has talked about and SpaceX has continued to demonstrate is a key factor in lowering that launch cost. And so that has a huge impact on our architecture.
Major paradigm shift.
It is. And so the way I've framed it in this paper is you're decreasing the cost per launch. So that's one of the C's. You're also increasing the cadence, the rate at which you can launch. You've also increased the confidence because you've demonstrated it time and time again, and you have a certain trust that you're going to get it to where you need to. But there's also the assessment of if I lose a dozen, 20, 40 of these smaller satellites, that's much less of a penalty than if I lost one of my massive billion dollar satellites, right? And so there is some level of
risk acceptance or attrition tolerance that is built into this new paradigm.
So it's a balance in the confidence. And then the capacity is the last issue that I talk about in the paper. And that is how much mass you can get up with that rocket. And we've talked about the smalls versus the mediums. The fairing size on top of the rocket, that has a lot to do with the capacity of the size of the satellites or satellite or satellites that you can put in orbit. So those are the 4 C's that I like to look at.
It's really interesting to think about how that cost really imposed a certain architecture that, and frankly, this broader paradigm of having the super exquisite gazillion dollar satellites, but now by bringing down the cost, increasing cadence, increasing confidence, and being able to dial the necessary rocket capacity. But if you think about the total launch capacity and aggregate across all of the launches, we are in a new space world.
Absolutely. It is a very exciting time to be in space for sure.
Yeah, it's like hugely dynamic, very exciting. So, Brad, how's a company like Ursa Major looking at all these factors when you develop your rocket engines? Is there one of these of the confidence, capacity, cadence, and cost that is preeminent from your perspective?
Yeah, I really like the 4 C's framework. It's helpful to think about priorities and how they might be important to phase over time. So to me, the cadence aspect, it has a fascinating relationship with the other C's. And if I were to prioritize one over the other, it would be that one. What's interesting is if you think about the cost and schedule to get to day one, the first flight of a particular launch vehicle, if you prioritize confidence, right? Very extensive degrees of mission assurance and reliability analysis and testing and all that. That's very good, but you're very likely to add schedule and cost to do so. If you really focus on cadence, getting to launch first, learning, having a healthy feedback loop for block upgrades, what you're going to find is confidence will come over time. So in other words, cadence begets confidence, and that's certainly the story of Falcon 9. It started off with some high risk missions and then upgraded along the way to get where it is today as this workhorse. And so when we think about cadence, it's also, maybe helpful to think for a moment of what cadence do we need in the launch market? And this is where commercial drives potentially a little bit more than the government side. Falcon 9, very impressive, on track for 120 or so launches this year, driven in large part by the Starlink constellation. If you look worldwide, somebody did an analysis recently that there are approximately 300 constellations planned across the world. And if everybody got to launch every satellite they wanted to within those, you'd be talking about 1 million satellites in low Earth orbit. Right.
And block out the sun.
Exactly. And while I don't think any of us really think that that's going to happen,
Yeah.
it's instructive to maybe benchmark it and say, okay, well, maybe let's just pretend 10% of those are realistic and can be launched, and make another assumption that's spread out over 10 years, that it's going to be a little bit slower to deploying than some of them are hoping for. If you make certain assumptions about the mass of each of these LEO satellites, you end up with, approaching 5,000 tons of mass needing to be launched every year. And that's like the equivalent of like 300 Falcon 9s.
Wow.
And so that's, roughly tripling the capacity there today. And so obviously these are very rough estimates, and the projecting out launch demand is notoriously a tough endeavor. The FAA back in 2014 did a 10-year projection of launch cadence and projected 28 commercial launches in 2023. And I don't want to pick on them because they tragically had to make that estimate a year or two before Starlink, the Starlink plans were fully formed. But obviously, there are 220 launches last year, and the majority of those are commercial. So it's a tough thing to predict, but I think it's safe to say that many multiples, I'll throw out tripling, but who knows what the real number will be, of demand for launch are gonna be there. And that's another reason why I take it back to cadence. And then that has specific technology implications. Another reason I'll bring up reusability is when you're engineering these launch systems and you see just the magnificent technical components that come together, and then you see an expendable launch and it all gets crashed into the ocean, right? It just doesn't make sense when you look at all the durable engineering that's going into these systems. And then if you're a P&L manager, really it makes even less sense to be throwing away what you could reuse. And so that's why we're focused on high performance reusable rocket engines. The high performance helps you recover the vehicle in the first place. And then the reusability aspect means we'll pay extra attention to sensitive life components like the turbines, the thrust chambers. There are certain fatigue limited components that need special attention in the architecture phase.
Yeah, Brad, I'm really glad you brought up the customer demand for launch, because if there's excess launch capacity and not enough launch demand, some of those launch companies will probably go out of business. And if there is over demand by satellite providers for launch and they can't meet that demand, then some of those satellite companies are probably going to go out of business. And all of that then limits what sort of architecture or capabilities the United States can leverage for its advantage. And so matching up that dynamic pull and push of customer demand, launch provider availability is really an interesting and complicated problem set. It's a dynamic problem.
But that balance is really important, and not just from a launch provider and satellite provider sort of commercial relationship and commercial balance, but frankly, that cadence, Brad, that you mentioned is really important from a military perspective and operational perspective regarding mission responsiveness. We've got to be able to have the right cadence with the right sized rocket to be able to do the mission when necessary and in real time. So this really kind of means a variety of launch approaches. And we've been talking about this today, from full expendable, reusable boosters, reusable upper stages, sea launch, air launch. So what have we learned about these ventures and these types of approaches, and how do they continue to shape the future of launch?
Yeah, I think the ways that we've looked at getting things to orbit in the past is going to continue to shape the ways we continue to look at opportunities in the future, right? Sea launch was a great prospect, and the benefit there is you could launch into any azimuth, sort of a free range in the Pacific, but there were some logistics concerns associated with getting the payloads and everything out there, and ultimately sea launch.
I could see how that'd be pretty hard.
Yeah, it was pretty hard. Air launch is another option to go into multiple azimuths, and but that leads to smaller. We talked about stratolaunch with two 747s basically stitched together. It's still not a massive rocket like the Starship.
And you bring up a really important point that where you launch out of and the kind of rocket that you have limits the orbital location and trajectory that you can get that payload to.
Yeah, absolutely.
Brad, was there anything you wanted to add there?
I think that one of the evolutions we're hoping to see in the launch industry is really having multiple high cadence launchers and launch sites come to bear. Yeah, and I think that there's a certain technology set that's important, that's helpful there, reusability. But there's Also, an important launch site aspect there of the launches in the world today, and up to date, I think we're at like 221 today. The United States accounts for about 57% of the launches to date in the world, and China's at 25%. But if you look under the hood at that 57%, I believe it's about 92% are SpaceX, and that's nearly all Falcon 9.
Wow.
And
That's a very niche capability. Whereas when you take a look under the hood at what China's launching, what kind of capabilities are they launching?
Yeah. Well, and I know we're here to talk about the launch paper that just came out, but last year I did a counter space paper and compared the capabilities of China and the United States. And when you take out the launch rate associated with Starlink, China is outpacing us pretty significantly in launch capability. And what China is launching is intelligence, surveillance, reconnaissance satellites, not just communication satellites. And so when it comes to Chinese launch capabilities, they really have 4 primary terrestrial locations, and they have a sea launch capability. They've got a dozen or so variations of the Long March rocket. And so they're actually a fairly robust launch provider. And as Brad pointed out, roughly a quarter of the global launches. What I think is really interesting is China's philosophy about launch. In the United States, we do not launch over populated areas, right? So that we launch to the east out of the East Coast, we launch to the west and south out of the West Coast. China launches over land. They've launched over cities, and when they've had anomalies, they have actually had debris fall onto cities and villages. And it's interesting because there was a launch recently that debris fell onto a village, but it got the payload to orbit, and China declared it a complete success.
Successful.
Right? That's a successful launch. This past summer, China launched part of its proliferated low Earth orbit constellation. And in the deployment of their satellites, they produced something like 700 pieces of debris. That was a complete success in their mind because they got the payload to orbit. So they're so focused on gaining an advantage over the United States and becoming the preeminent space power on the planet that they are putting a lot of those risk factors aside. And I'm not saying that the United States should do that. Absolutely not. But I think it speaks volumes about the extent to which China will go to achieve the advantage that they think is so crucial to them as a nation.
Yeah, we need to be careful to not mirror image their, what we would do onto what we expect their behavior to be. They'll try to achieve that advantage kind of no matter what. Brad, what is there a key distinction from an industrial perspective that strikes you when you compare U.S. and Chinese launch?
Yeah, I think that the theme when you look at Chinese launch in contrast to US is there's a lot of diversity. So Charles talked to the launch sites, and of the 4 land-based sites, only one is actually on that southern island of Hainan. And at each site, there's multiple pads, maybe about 15 or more operational. They've got the Yellow Sea sea launch operations going. And so there's just geographically a lot of diversity. But on the vehicle side itself, there is no such concentration of any vehicle launching 90% of the capacity, or the cadence. The US this year had 2 different vehicles that launched from US soil 4 times or more, and that's Falcon 9 and actually Starship. There's a little bit of time left. Maybe some others clear that mark, but just by contrast, China's had I believe 5 or 6 different families with at least 4 different launches this year.
Wow.
So those tend to be basically the Long March series that Charles alluded to, and within that series, you have all different types of technology: hypergolic propellants, kerosene, solid rocket boosters. There's hydrogen upper stages. So it's really split across 6 different vehicle families or more, 5 different launch sites. And that's just actually kind of like the government side of operations. There's the quote unquote commercial side of Chinese launch, which is doesn't always get covered, but it's actually burgeoning. There's a lot of inspiration one way or another from what SpaceX is doing, and there's a lot of Chinese companies working on reusable launch systems. Several of them have launched this year. They were actually the first to launch an orbital methane vehicle last year in 2023. And so, I mean, you add it all up, and on a sheer cadence basis, the U.S. has superiority, but on diversity of technologies and launch sites and organizations launching, China's really got some capability there.
Yeah, and we talked earlier about the interplay between the four C's, and you're right, Brad. The cadence and the diversification also offers some confidence. And so let me dive into that a little bit more. The two of the three NNSL providers or would-be providers both use the same BE4 engine on their first stage. If there's ever a problem with that, we're going to be grounding 2/3 of our potential NNSL fleet.
I'm glad you brought that up, because I was going to say, like, diversification is a really important piece of having resilience and survivability and a capability.
Absolutely. And so that's resilience and diversification from the booster itself and also the launch location. We did a workshop at the end of October here at the Mitchell Institute, and one of the crises that we threw at our participants was what we call the triple threat, and it was how to maintain awareness over a potential rise in aggression over in the Western Pacific, while there was a hurricane that came through Central Florida and knocked out our launch capability, while there was an on-orbit debris event. And I was feeling particularly sadistic, I think, when I came up with that scenario. But the participants unanimously looked at how do we regain our launch capability.
Well, I was there, and it was a really incredible workshop, and a lot of the teams came up with diversifying launch locations.
Absolutely. They came up with diversifying launch location, not just within the CONUS in the United States,
but across
also
allies and partners.
Exactly, and which is such a key part of the Space Force architecture right now and strategy is the integration of allies and partners. And so there are other launch providers out there, the European Space Agency, Scotland, New Zealand. There are a lot of other countries out there that are pursuing launch, and there are allies. And so maybe that's an area that we need to be investing some more policy.
I was just going to say, I think policy was a key element that needs to be addressed to empower and enable not just U.S. government launches, but commercial launches as well, where here we've got the Missile Technology Control Regime preventing us from sharing a lot of the engine technologies and launch capabilities across partners, even if they're also members of the regime. So it's time for us to be able to change and re-envision what are the right policies that we need to have as a U.S. government to empower and strengthen our launch capabilities, the diversification, and locations across all of our allies and partners. So we know launch is important. And China, as you gentlemen have been discussing, is, we say that they're trying to catch up and surpass us, but I think you've just made the case that in many ways they already have in terms of diversification, engine types, and locations. What should the Space Force do to ensure that we stay ahead?
I think as a first clear priority, the Space Force budget does need to be increased. The area of responsibility is vast. We have companies deploying capital to get launchers online, but there are areas where we can incentivize technologies and capability for high cadence, and I think is important. There are other low-hanging fruit items and priority areas the Space Force could think more about. That includes international collaboration. There's some low-hanging fruit there where we can ease export control classifications and really improve the national immunity and resilience of the launch supply chain by opening up collaboration with partners, and it includes vehicles and launch sites. And then also risk tolerance. That is an available knob to help get to first flight, get that learning loop going for new launchers.
Yeah, I definitely agree with that. And while throwing money at the problem isn't always the right answer, I do think we need to continue to invest in research and development when it comes to rocket technology so that we continue to develop what's next. So I think that's a critical area. Launch diversification, both within the United States as well as with international partners, is going to be a key factor. And I think monitoring the supply chain. When there's a component that affects multiple launch vehicles, I know it's up to the prime, right, or the rocket provider to monitor their own supply chain. But if somebody in the government isn't also aware of the criticality of some component or some raw material, they may make decisions that are ill-informed. And so I just encourage those that have that type of sway to understand where our choke points are in terms of the supply chain.
That's really important because you could have suppliers that are vendors to multiple primes, but if the primes don't have insight into that demand across the entire industry, that creates a risk. So let's just wrap this up while describing risk, because I think the 4Cs are intended to be able to address that through a variety of different approaches. But right now, we have to be conscientious of the risk of launch failure, risk of losing our space advantage, and we have to be able to minimize the consequences when those risks actually happen. And the space community is historically known for being very risk averse, and we talked about this a little bit regarding confidence and cadence and cost and so forth. How do you see the risk tolerance of the Space Force and the nation evolving to be able to achieve the type of launch environment and ecosystem that we need?
So I think the risk story of space launch has evolved over time. It's important to acknowledge that the formation of NSSL Lane 1 is a good start to try to optimize which payloads really need which level of risk. But, I think basically it just needs to be cemented in really as many acquisition platforms as possible. I think back to earlier Falcon 9 development, there's something of a comfort level today with national security launch, in large part due to the high cadence that Falcon 9 is able to deliver. But of course, that started out with being an extraordinarily risky set of missions, of demo missions, a decade or more ago to get to where it is today. And I will say even riskier than some of the requirements that are posed in Lane 1, right? So it's still not quite as risk tolerant as the conditions that existed to get Falcon 9 where it is today. And so I just think that I talked about the two knobs that Space Force might be able to address near term before budget increases are available. And then I think it's international collaboration and the risk knob. Those are more direct items that are able to be controlled.
Yeah, so we talked earlier about the legacy architecture and how it was very risk averse, and how the move to proliferation and lower cost satellites helps increase our risk tolerance. And if one launch fails and we lose 40 small satellites, that's a much more palatable loss than $1 billion single system. We don't ever want to have a launch failure, but we have to plan for an architecture that can both withstand that and recover from it, and then have some built-in resilience in the event that there is a single launch vehicle that gets grounded. We don't want to ground the entire fleet. And so when we look at risk, we have to look at the risk of a specific mission. We have launch mission, that is, and we also have to look at the risk of the overall mission that's being deployed. And we have to look at the risk of the entire space architecture and the ramifications for our nation in the great power competition with China.
Definitely a conversation we'll continue more. Gentlemen, thank you so much for joining us. For our listeners, we will include links to both of Charles's reports in the show notes. And if I can, we'll also post a picture of his socks. He's really understood the assignment today with his space socks. So again, I can't thank you both enough for joining us today and helping us understand launch.
Thanks, Heather.
Thank you.
With that, I'd like to extend a big thank you to our guests for joining in today's discussion. I'd also like to extend a big thank you to you, our listeners, for your continued support and for tuning into today's show. If you like what you heard today, don't forget to hit that like button and follow or subscribe to the Aerospace Advantage. You can also leave a comment to let us know what you think about our show or areas you would like us to explore further. As always, you can join in on the conversation by following the Mitchell Institute on Twitter, Instagram, Facebook, or LinkedIn, and you can always find us at mitchellaerospacepower.org. Thanks again for joining us, and have a great aerospace power kind of day. See you next time. Okay, Brad, just got to ask, are you wearing space socks today?
I unfortunately, that memo got lost in the mail.
Come on, man. You need to understand the assignment. We can't even see you. You're on Zoom. Send us pictures of some space socks.
I will do my best tomorrow.
Awesome. All right. Well, you got 4 minutes to go. Again, thank you so much.
Thanks, Brad.
I think we're good, and we'll let you go on to your 1:30.
All right.
Or whatever
Thanks.
30 it is where you are.
Yeah.